Hello friends, welcome back to my channel Computer Engineering Made Easy, and I am Anindita. In this tutorial, we will be learning about the concept of structures using the C language. A structure is basically a user-defined data type that allows us to combine data items of different kinds. It is used to represent a record in a database. Anything that is a common noun can be considered as a record and hence a structure. Entities that define the characteristics of the record to make it a proper noun from a common noun can be considered as the structure members. For example, if we have a book, book is a common noun. However, if we specify the informations like the title of the book, the author of the book, the publisher of the book, the volume of the book, etc., then we can characterize the book and form a proper noun. Hence, the book can be considered to be the structure name, while the title, the author, the publisher, and the volume, etc., can be considered as the members of the structure book. Now let us consider how can we store the information in a structure. If we consider storing information about one book, we can have four different character arrays by the name of title, publisher, author, and the volume to store the information of the book. However, if we now consider storing the information of 5 books, we can consider four 5 cross n size character arrays. However, if we have to store the information of about 10 lakh books or even more, can we handle it by using four 10 lakh cross n sized arrays? Will it be easy to track and handle? Definitely not, right? This is where a structure comes to our rescue. We can declare a structure by writing struct book followed by the members of the structure, which in this case are char title 50, character array for holding the author of size 50, another character array for storing the publisher of size 100, and another character array for holding the volume of size 10. Note that the declaration of a structure ends with a semicolon. Here, in this statement, the struct is basically a keyword which defines the structure, and we can map the struct book to the system-defined data type like float or int. Similarly, we can define another structure, student, which identifies the information of individual student. And for that, we can write struct student with its members as a character array called name of size 50, which will be responsible for holding the name of the student, an integer value for the roll number, and a marks array of size 8 cross 5, considering that this array will be storing the marks of the student for 8 semesters, considering each semester has got 5 subjects. So therefore, just like we can write the system-defined data type float, int, double, etc., now we can consider a user-defined data type as struct book or struct student. Now that we have defined the user-defined data type, how can we declare variables of this user-defined data type? There are two methods for doing so. In the first method, we can simply just write the variable names right after the declaration of the structure followed by a semicolon, as shown in the slide. In the second method, we can write struct student, that is the user-defined data type, inside the main function followed by the list of variables, just like we do in case of system-defined variables. Like we can write int ij. Now, instead of int, we write struct student because that is the user-defined data type. And following the struct student, we can write the variable names as s1, s2, s3, etc. In either case, the scope of the variable depends upon where exactly the declaration has been made. If the method 1 is adopted and struct student data type is defined outside the main function, then s1, s2, and s3 are going to be global variables, whereas in case of method 2, where struct student s1, s2, and s3 are declared inside the main function, the variables s1, s2, and s3 have their scope within the main function only. In either case, the structure of the variable in the memory looks somewhat like this. As shown in the figure, here we have got one single variable s1, and inside the variable s1, we have 3 different parts. The first part is responsible for holding the roll number, which is an integer value. The second part is responsible for holding the name of the student. This is a character array. And the third part is responsible for holding the 8 semester marks of the student, and this is also a integer array. Now, if we have 3 students, we can handle the details of those 3 students using the 3 variables S1, S2 and S3. But now, say if we have a huge number of students, for example, say 800 students. So for 800 students, is declaring 800 variables a feasible option? Definitely not, right? So that is where the concept of array of structures come into the picture. Now, in order to declare an array of integers, we simply write int arr 800. That itself creates a static array arr of type integer, which has 800 cells. Similarly, in order to create an array of structures, we simply write the user-defined data type followed by the name of the array and the size of the array. In this case, the user-defined data type is struct student. So instead of int, we simply write struct student, replacing the data type. S is the name of the array and 800 is the size of the array. Once we create this struct student S array, we get an array S comprising of 800 cells, where each cell has 3 members, that is the roll number, the name and the marks. Now that the array has been created, let us take a look as how we can store data inside this array. We can store data inside structure variables using 2 operators. The first one is the dot operator and the second one is the arrow operator. The dot operator is used to access the structure members using structure variables, whereas the arrow operator is used to access the structure members by a pointer to a structure or by the address of a structure variable. In both the cases, we will see how we can access a single variable as well as array of structures. In this example, let us see how we can access the structure members of a single structure variable. Let us consider that we want to store the 8 semester marks of a student, considering that there are 5 subjects per semester. Accordingly, we define the macros sem as 8 and subpersem as 5. In order to declare the variable of type structure student, we write struct student S1. Next, we ask the user to enter the roll number and the name of the student. The name and the roll number of the student are stored as s1.roll and s1.name in the structure S1, where roll, name and marks are all members of the structure student. Similarly, when we intend to display the output, again we access the individual members of the structure variable S1 using the dot operator. So in order to display the roll, we access s1.roll. In order to access the name, we write s1.name. And in order to access the marks of the ith sim and jth subject, we write s1.marks ij. The output of the given code will be as expected. However, the main aspect to note here is that the variable S1 is created in the stack memory. Also, the individual members, roll, name, and marks can be accessed very well inside the stack memory. This can be seen easily from the watches window of the code blocks IDE. Moving on to the next example, here we intend to access the individual structure members from a static array of structures. Now, a static array of structure can be declared by simply writing the user-defined data type followed by the name of the array and the size of the array. So therefore, if we write struct student S1 std count, this is going to create an array of structure student named S1 and size student count. Once the array has been created, we can access the individual cells of the array using a normal loop, just like we do in case of a normal array. So if we have an integer array, say int arr100, we can access the ith cell of the array by writing a of I. Similarly, here we can access the individual cell of the array of structures by writing s1 of k. Now, once we reach the kth cell of the array, we can access the members of that particular cell, that is the roll, name, and marks using the dot operator. Therefore, for each student, Here, when we take the value of roll number, name, and marks as input from the user, we can simply write ampersand S1 of k, indicating the kth cell of the array S1, and then followed by dot roll, dot name, or dot marks, indicating which particular member of the structure we want to access. So therefore, ampersand S1 of k dot roll will store the roll number taken as input from the user in the roll number field of the kth cell of the S1 array. Similarly, ampersand S1k dot name will store the name taken as input from the user in the name field of the kth cell of the array S1. Similarly, when we want to display the content of the array, we use S1 of k dot roll to display the roll number of the kth cell of the array, S1 k dot name to represent or display the name of the kth cell of the array, and similarly for marks we write S1 k dot marks ij. Even in this case, the output will be as expected. But what is interesting to see is how this array of structure S1 is stored in the stack memory. This can again be seen from the watches window by enabling the debugger in CodeBlocks IDE. Here, as we can see, the array of structure S1 has been created statically inside the stack memory, and each of its cell can be observed as 0, 1, 2, and 3. Once we find the cells, we can see that for each cell, there exists separate fields for roll number, name, and marks. So therefore, the entire array of the structure, that is S1, is stored in the stack memory and is clearly visible in the watches window. Thus, from the examples that we have discussed till now, we have seen that if the structure is created in the stack memory, we can access its elements by using the dot operator. Next, we will see a set of examples where we will be creating the structure variables in the heap memory, and hence we will be using the arrow operator to access its individual members. In this example, we will be accessing a structure variable using a pointer to a structure. In this case, the structure variable will be created in the heap memory, and we will access the variable using a pointer from the stack memory. In order to do so, we first need to create a pointer to a structure which is created by the statement struct student star S1. By this statement, a pointer to a structure variable is created in the stack memory. However, this variable at this point of time holds just garbage value. The members of the structure will acquire memory once memory is allocated to them using the malloc function. So once we execute the statement S1 equal to struct student star malloc size of struct student, a chunk of memory of the size of struct student is allocated in the heap memory, and the base address of this memory chunk is stored in the variable S1 in the stack memory. In the heap memory, space has been assigned for the individual members of the structure like the role, name, and the marks. Accordingly, we can store data in the structure members using ampersand S1 arrow role, ampersand S1 arrow name, and ampersand S1 arrow marks. Here, the arrow operator allows us to access the members of the structure variables which are actually located in the heap memory. Finally, when we want to display the content of the variable, we can again display them using the pointer S1 and using the arrow operator. So S1 arrow role, S1 arrow name, and S1 arrow marks is going to display the content of the variable to the user. The output of this particular program will be as expected. However, if we take a look into the watches window of the CodeBlocks IDE during the execution, we will find that in the stack memory, we only have the variable S1 which is holding a memory address. In order to see the content of the structure members of the variable that has been assigned in the heap memory, we can explicitly type in S1 arrow role and S1 arrow name to see the values stored in those positions. Now that we have understood how a structure variable can be created dynamically in the heap memory, we will take a look at an example where we can create an array of structure dynamically in the heap memory. In this example, we will create a variable of pointer to a structure type in the stack memory, and then using the malloc function, we will create an array of structure in the heap memory. So accordingly, the pointer to structure variable here in this case is declared as struct student star s1. S1 occupies its location in the stack memory. And next, we create an array of size stdcnt in the heap memory. The array in the heap memory is created using the statement s1 equal to struct student star malloc size of struct student into std count. This particular statement creates an array of structures of size 4 in the heap memory, and the base address is stored in the variable s1. Now, S1 therefore holds the address of the 0th location or the 0th cell of the array of structures. Now, in order to store data inside each of these cells of the array of structures, we first run a loop for k equal to 0 to k less than stdcnt. Here, k indicates the cell number of the array of structure where we want to store the data. In order to reach a particular cell in the heap memory, we write s1 plus k. Therefore, using the pointer arithmetic, we can reach to the address of the kth cell of the array. Once we reach the kth cell of the array, then we can refer to the individual structure members of that particular cell using the arrow operator. Accordingly, when we take the values as input from the user in order to store the roll number in the kth cell of the array, we write scanf%t ampersand s1 plus k arrow roll. Note that even if s1 plus k is referring to an address, s1 plus k arrow roll is referring to a particular variable, and hence the ampersand here provides us with the address of the specific variable. Similarly, for the name also, we write ampersand s1 plus k arrow name. On the other hand, when we intend to display the values of the members of the structure of the kth cell of the array, we write printf%d, then s1 plus k arrow marks of ij, or s1 plus k arrow roll number, or s1 plus k arrow name. This is how we access the individual structure members of each cell of the array of structures. The output of this particular example is also as expected, and if we take a deeper look at the problem using the watches window, we will find that the variable s1 is holding only the memory address of the 0th cell of the array that has been created, and the individual members of the kth cell can be accessed by explicitly typing s1 plus k arrow followed by the roll name or other members of the structure that has been declared earlier. Now, if we create a user-defined data type as struct student, and we have to write a program where we have to use this data type quite a number of times, typing struct student for multiple number of times might be a tedious job. Hence, in order to make our life easier, C has provided us with another keyword called the typedef keyword. Hence, the discussion related to the typedef keyword is often associated with discussion on structures. The typedef keyword is used to give a new name to a system-defined data type or a user-defined data type. For example, we can write typedef unsigned char byte. If we write this, this means we are renaming the data type unsigned char as byte. So therefore, if we want to further declare variables of type unsigned char, we can easily write byte b1, b2. In this case, both the variables b1 and b2 will be of type unsigned char even if they appear to be of type byte. Typedef therefore creates alias of a data type. In context of structures, we can use the typedef keyword in two ways. In the first method, we can create an alias of the structure that we are defining right when we declare it. For example, instead of writing struct student int roll char name and int marks, we can write typedef struct student int roll char name int marks followed by the new name that we will be giving to this struct student data type, which in this case is stud. This means From this point onwards, wherever we write stud, we actually mean struct student. So stud becomes an abbreviation of struct student and can hence be used throughout the program when and where required. So in order to declare a variable of type pointer to struct student, we can simply write stud star s1. S1 here is a pointer to a structure student type of variable. Also, when we allocate memory to the variable S1, we again write stud star instead of struct student star and size of stud instead of size of struct student. Typedef can also be used in another way. Instead of defining the alias during the structure declaration, we can define the alias after the structure declaration as well. In this case, as you can see in the example, we have written typedef struct student stud after the structure student has been defined. So from this point onwards, where the typedef statement executes, we can write struct student as stud throughout the program. Next, we will see how we can pass structures to functions. Structures can be passed to functions in 4 different ways. In the first method, we will see how we can pass the structure members as values to functions. Next, we will see how we can pass the structure variable as a whole as value to a function. In the third case, we will see how we can pass the address of a structure variable to a function. And finally, we shall see how we can pass array of structures created dynamically into a function. In order to understand how we can pass the structure members as values to a function, we create a structure called val by writing struct val, and inside that we leave 2 members int a and int b. Next, we declare a function int add1 which takes in 2 parameters of type integer and returns back the sum of the 2 integers passed as parameters back to the main function. In the main function, we declare a variable of type struct val called v1 and also a variable of type integer called s. Next, we take 2 numbers as input from the user which are stored in the members a and b of the variable v1. Next, we call the function add1 while passing v1.a and v1.b as parameters to the function add1. Note that here we are passing the members of the structure variable v1 as values to the function add1. In the function add1, the value stored in v1.a gets copied into the local variable p, and the value of the variable v1.b gets copied into the local variable q. The function add1 returns the sum of p and q back to the main function, which gets stored in the variable s. Finally, we display the value of the variable s. In case we want to pass the structure variable as a whole as value to the function, we need to declare the function add2, which in this case will be taking a struct val type of variable as a parameter. Hence, we declare the function add2 as int add2 struct val. Again, in the main function, we create a variable v1 of type struct val, and we take 2 numbers as input from the user which are stored as the members a and b of the variable v1. Next, when we call the function add2, instead of passing v1.a or v1.b, that is the structure members, we now pass v1, which is of type struct val. In the function add2, we also need a local variable of type struct val to hold whatever is being passed from the main function to the function add2. Hence, we have the variable p declared in the function add2 of data type struct val. The function add2 then performs the addition of the members a and b of the variable p by doing p.a plus p.b, and the sum is then returned back to the main function, which is stored in the variable s and thereby printed in the main function. Now we will see how we can pass the address of the structure variable. Here, 2 things may happen. The variable whose address we intend to pass may be located in the stack memory or in the heap memory. In the first example, we will see where a variable v1 is created in the stack memory. So if we declare a variable v1 of type struct val in the main function, this means this variable v1 will be located in the stack memory. Then we take two values as input from the user and we store it in the members A and B of the variable v1. Next, when we call the function add3, note that here add3 has been declared as int add3 struct val star. That means this function add3 is capable of taking the address of a variable of struct val type. So when we call the function add3 from the main function, in the first case we pass the address of the variable v1. In the function add3, note that we access the individual member variables of the structure val using the address p. Since we are accessing the structure members using the address that is stored in the variable p, we use the arrow operator here to access the variables. Therefore, in order to perform the sum, we write p arrow a plus p arrow b. Finally, the sum, which is again an integer value, is returned back to the main function and is stored in the variable s, which is then displayed to the user. In this case, variable v1 is in the stack memory because we haven't used malloc to allocate memory to v1. In the second case, see that we have declared a variable v3 which is of type struct val star. This means v3 is basically a pointer type of variable which is a pointer to a structure val. Next, we assign memory to v3 from the heap using the malloc function by writing the statement v3 equal to struct val star malloc size of struct val. This means that the variable v3 is located in the stack memory, but actually the member variables, that is a and b, which are associated with the variable v3 are located in the heap memory. When we ask the user to provide us with two numbers as input, note that in the scanf statement we are using @ of v3 arrow a and @ v3 arrow b instead of using the dot operator. While in the case of stack memory, for the scanf statement we had used the dot operator, that is &v1 dot a and &v1 dot b. But now, since a and b are located in the heap memory, we are using the arrow operators to access them. Next, we call the function add3 and we pass the variable v3. v3 is holding the address of the entire chunk of memory that has been assigned. In the function add3, see, here we are again accessing the members a and b using the arrow operator, and their sum is performed by p arrow a plus p arrow b, and the sum is returned back to the main function. The sum is an integer value and hence the variable s can hold it easily. Finally, we display the value. So overall, we can say that if x is an address, then in order to access the internal members of x, we have to use x arrow a and x arrow b. However, if x is a variable, then in that case, we have to use x dot a and x dot b to access the internal members. Now moving on to the next example, we shall see how we can pass array of structures to function and then return array back to the main function. So for this, we are considering that we have a variable of type integer called n in the main function, which takes the size of the array of structure to be formed. Accordingly, depending upon the value of n, which in this case we have considered to be 5, we create array of structures of size 5. Here in this array of structure, each cell has got two variables or two members, that is a and b, who are capable of holding integers. The array is created dynamically and hence the entire memory chunk is occupied from the heap memory, while the base address is being held in the pointer to structure variable called v3 in the stack memory. Now, when the function add is called, the variable n and the address stored in the variable v3 are passed as the parameters to the function add. Accordingly, local variables are created in the add function by the name of n, which is basically an integer, and a pointer to a structure called p. The address of the array of structure, which in this case is 1200, gets copied into the variable p, while the value n, that is the size of the array of structure, gets copied into the variable n of the add function. Accordingly, in the add function, the array of structure is explored, and for each cell, the sum of the two members is calculated and stored in the corresponding cell of a dynamically created integer array in the function add. Since the array is created dynamically, again, the base address of the array is stored in a local variable s in the scope of the function add. Once the computation of the sum of the members of each cell of the array of structure has been completed and updated in the corresponding cells in the integer array, the base address of the integer array that is stored in the variable s is returned back to the main function. Once the control comes back to the main function, all variables in scope of the add function gets removed from the stack. However, the integer array still remains as it is located in the heap. And since its reference is passed back to the or returned back to the main function, we can easily access each and every element of the integer array from the variable s, which is located in the main function. Let's now take a look at the code of this particular program. Firstly, we create the structure called struct val, which has got two variables, int a and int b. Now we declare the function add4, which will be responsible for creating the array of integers and will be responsible for calculating the sum of a and b of each cell of the array of structure and store it in the corresponding cell in the integer array. Note that the prototype declaration of the function add4 is int star add4 struct val star comma int. Struct val star here is given because we will be passing the base address of the array of structures. Int is passed as the number of cells of the array, and int star is being returned from the add4 function because here we will be returning back the base address of the integer array that has been created dynamically in the function add4. Coming to the main function, we first declare a pointer to the structure variable struct val called v3. We also declare a pointer to an integer s and two integer variables n and I. N is hard-coded to be 5. We can also take the value of n as input from the user, and accordingly in the statement v3 equal to struct val star malloc n into size of struct val, we create an array of structures of size 5 whose base address now gets stored in the variable v3. Now we run this loop for I equal to 0 to I less than n to take numbers as input for each and every cell of the array of structures and accordingly store it in the corresponding member locations. Note that here v3 is holding the address of a particular cell, or that is the base cell. And when we add I to v3, that itself also provides us with an address. However, when we write this address arrow a, we are referring to a particular variable. Hence, we need to precede it with an ampersand when we write the scanf function. Hence, we write scanf %d ampersand v3 plus I arrow a ampersand v3 plus I arrow b. This statement is going to allow us to store data or integer values in the individual members of each cell of the array of structures. Once data has been stored in the array of structures, we next call the function s is equals to add4 v3n. Here v3, that is the base address of the array of structures, and the value of the number n is being passed as parameters. In the function add4, we create another integer array given by s is equals to int star malloc n into size of int. That means that we have created the array dynamically. And then we run this loop for I equal to 0 to I less than ni plus plus, where we access individual elements or individual members of each cell of the array of structures. We add them and then we store their sum in the corresponding cell of the integer array. Finally, we return the base address of the array of integers, which is then used to access the individual elements of the array of integers and display it from the main function. With that, we come to the end of our tutorial on structures. If you like my presentation, if you have gathered any knowledge from my presentation, please make sure to hit the like button and subscribe to my channel for more such videos. Don't forget to hit the bell icon for further notifications. Thank you. We'll see you again. Till then, goodbye.